So continuing with the applications of the residue theorem to real integrals, we're going to be looking at a particular problem today. So that's going to be the following definite integral that is going to go from minus infinity to infinity. And the function is going to be 1 over x to the power of 4 plus 4 dx. So normally we would look at this and we would try to factorize the denominator such that we can use partial fractions to reduce this expression to something we can integrate more easily. But in this case, this is going to be fairly complicated because we have an x to the power of 4 here. So what we can actually do is we can cast this into a complex integral, a contour integral, by making use of the following definition. Because we have limits from minus infinity to infinity, what we can do is we can define a semicircle on the complex plane that is going to have the following property. So it's going to go from minus r to r, so that's going to be the radius of the circle, semicircle centered at the origin. And basically we're going to let r go to infinity, such that it meets the condition that the boundaries of integration are going to be minus infinity and infinity. So what we can do with this is we can define the contour as basically being this semicircle, and then we're going to take the poles of this. We're going to replace every x or every variable that we integrate with respect to by z, and then every pole that lies on top of this, on the top half of this plane, we're going to take the residue of, and everything that lies below the real axis we're just going to ignore. The rest is just going to be 0. And there's a lot of mathematical derivation and definitions behind that I won't go into. Basically, you just need to know that essentially we just care about the residues that lie either on top of the real axis or right on the real axis. So basically that's what we're going to be looking at. So let's replace this expression by a complex integral. So the contour is going to be this, and we're going to have this z over z to the power of 4 plus 4. So this is going to be the integral we're going to be solving. And having the integral in this form will basically allow us to find the residues, and by calculating the residues we can find the principal value, which is often called the principal Cauchy value of the integral, which is just the value of that integral. So let's proceed and do that. So basically what we're going to do is we're going to factorize the bottom. So we want to write the expression z to the power 4 plus 4 equals to 0, and that means that z to the power 4 is going to be equal to minus 4. Now this means that we're going to have another complex number that is going to be defined by this. So what we can do is we can try and express this in polar form to see what we get. Remember that we want to get the value of z. So this is going to be the 4th roots of the number 1 over 4. And as we did in one of the first videos in this series, where we talked about how to find the roots of a particular complex number, even if it is just a real number, what we need to do is we need to first express this in exponential form. So we're going to find the magnitude of this complex number. So magnitude of this is going to be equal to square root of 4 squared. So this is just going to be 4. So it's going to be the magnitude, and then the angle that it makes with the horizontal, so on the complex plane. Basically this is minus 4 on the real axis, which means that our angle is going to be equal to pi. So now in order to find the 4th roots of 4 minus 4, which are going to give us the value of the complex number set, what we're going to have is the following. We're going to have 4 4th roots times e to the power of I. So we're going to have the angle pi plus 2k pi over 4, and we're going to remember that k is going to go from 0 all the way to n minus 1. So n is 4, that's going to be 3. So those are the 4 values of k, and each of those values of k is going to give us a different value for those roots. So now z is going to be equal to root 2, and this is going to be equal to e to the I pi over 4. So we start substituting for the values of k. This is going to be 3 pi on 4 root 2 e to the I 5 pi on 4, and then root 2 e to the I 7 pi on 4. So those are going to be the 4 roots from this, And basically what this represents is, because the roots of that equation, these are going to be the poles. These are going to be the values of the poles on our particular problem. And now what we're going to do is we're going to have the complex plane again. We're going to try and plot them. We're going to try to plot this. So we're going to have the unit circle. And then we're going to start plotting them. So the first one is going to be around here. So that's pi over 4. That's the angle from the real axis. That's I pi on 4. Then the second one is going to be around here. So that's root 2 e to the I 3 pi on 4. Then this one is going to be root 2 e I 5 pi on 4. And then finally we have root 2 e to the power of I 7 pi on 4. And we said that we only take into account whatever poles lie on top of the real axis. So this basically means that we're going to ignore these two, and our two poles are going to be these two. And now what we need to do is we need to write the function f of z as 1 over z minus root 2 e to the I pi on 4. So we're just going to factorize that denominator, minus root 2 e to the I 3 and pi on 4. And then we need to do the same for all four roots. So that's going to become the function. And just to rectify, this is not a unit circle. It's actually a circle of radius square root of 2. Because remember, this here, the magnitude of the complex, of the exponential form of the complex roots is going to be the radius of the circle. So this should be root 2 here everywhere. So minus root 2 minus root 2. So I just wanted to clarify that, because I just noticed that I defined this as a unit circle, when in reality the radius should be square root of 2. So now we have the function defined. What we can do is we can proceed to actually find the residues at the 2 points that actually lie on top of the real axis. And those 2 points are going to be these two here. So what we're going to do is we're going to find the residues of those. So we're going to go back here, and then let's just erase this for a second, just to make some room for our calculations. So basically, just to rewrite our function of z, we're going to have 1, and this is going to be a fairly long polynomial, because remember that we just factorized and we got 4 roots. So this is going to be minus root 2 e to the I pi on 4, z minus root 2 e to the I 3 pi on 4, z minus root 2 e to the I 5 pi on 4, z minus root 2 e to the I 7 pi on 4. So we're going to have this fairly long expression in the denominator, and we know that we're only going to get these two first ones are going to be the poles that we have, and they're both poles of order 1, so that simplifies the calculations for the residues. So residue of the function f of z at the point z equals to root 2 e to the I pi on 4. So that's just going to be the limit. So this is pole order 1, so that's just going to be the limit of z approaches root 2 e to the I pi on 4 of the following expression. So we're going to have this in the numerator, and then this whole expression in the denominator. So in the end, we're going to end up with the following. So this is a fairly long calculation. I won't go into it, because all you need to do essentially to get the value, to evaluate this expression, is put the values of z into here. So basically you're just going to put this value, and then you can evaluate these ones by using the expansion. So remember that the Euler identity tells us that this is going to be equal to cosine of theta plus I sine of theta. So what you're going to do is you're going to evaluate each of these roots in Cartesian form, and then you're just going to add the real and imaginary parts together, and hopefully in the end you will come up with the following answer. So this is going to give you this should actually give you the following value. So that's minus 1 over 16 minus I over 16. And then for the second residue, we're going to have the residue of the function f of z at the pole root 2 e to the I 3 pi on 4. And applying the same procedure as before, you're going to take the limit of the function times the pole. So this is going to be equal to 1 over 16 minus I on 16. And then in the end, what you're going to get is the following. You're going to get the following. So remember that we started off with this real integral, dx over x over 4, x to the power 4 plus 4. And we defined it as the complex integral on the unit, on the circle with radius infinity, on the upper half plane of the complex plane. So it was dz over z to the power 4 plus 4. And then basically this is going to be equal to 2 pi I times the sum of residues. In this case we have 2, so we're going to add this to that, and then we're going to multiply by 2 pi I, and then in the end it's going to give you pi on 4. So that's going to be the value of this real integral. So this is a really interesting application of complex analysis, and the residue theorem to evaluate in real integrals that have either infinite limits or that are impossible to calculate by using any other standard methods of integration. And hopefully this has given you an idea as to what the residue theorem and complex analysis in general can be applied to in terms of mathematics and calculus. There are a lot of other applications, such as inverting the Laplace transform, which I talk about in the series about differential equations, which makes use of the residue theorem as well. And there are some other transforms that you can invert using the residue theorem. One of them is the inverse set transform, which also makes use of the residue theorem, and I might cover this in a future video. But basically this is just to show you some of the main applications of complex analysis to solving practical problems in mathematics, and hopefully you have enjoyed this series. I might expand on it in the future, but this should give you a good enough idea of some of the applications and some of the problem solving techniques using complex analysis. So thank you for watching.